Hello, everyone. My name is Jingxiao Liu. I'm a PhD student at Stanford University. My talk for ICASSP is about some interesting work we have been doing to make use of vibration measurements collected on board vehicles as they travel through structures that require inspection. This work has been done by me and also by Siheng Chen from Carnegie Mellon University, Siheng Chen from Mitsubishi Research Lab, and Professors Berges, Jacobo Bielak from Carnegie Mellon University, and Professor HaeYoung Noh from Stanford University. Bridges are key components of the transportation infrastructure. However, in the United States, over 139,000 bridges were structurally deficient or functionally obsolete, and the number is still rising. Structural deficiency and functional obsolescence can lead to bridge failures, and therefore they need immediate attention. Bridge failures generally start from local and MERL damages. To prevent catastrophe, it is required to detect bridge deterioration early when the damages are MERLed. Early detection of MERL damages not only prevents bridge from collapsing, it can also save rehabilitation and traffic interruption related costs. To achieve early damage detection and track the deterioration progress, we need to conduct timely bridge inspection and bridge conditions monitoring. Manual inspections is the traditionally used method, which provides detailed assessment of the bridge, but it requires trained inspectors to walk through the bridge, which can incur high labor cost. Well, it cannot achieve timely damage detection. So to overcome the shortcomings, sensing methods are utilized. We directly install sensors such as accelerometers on bridges to continuously and autonomously monitor bridge health. However, as the lifespan of the sensing system is much shorter than that of the bridge, and the electrical system is vulnerable to the ambient environment, such method can also be costly, and it is required to on-site installation and maintenance. So in order to achieve a low-cost and timely bridge health monitoring, vehicle vibration-based bridge health monitoring has been introduced. Instead of installing sensor on the bridge, we install vibration sensors on the vehicle, drive the vehicle over the bridge, and collect the vertical dynamic response of the vehicle. Vehicle accelerations can capture the dynamic bridge-vehicle interaction features, and thus can indirectly capture the information about the dynamic characteristics of the bridge. This information can be used for damage detection, localization, and quantification. This indirect sensing method allows us to achieve relatively timely monitoring with low cost and low maintenance, because there is no need to stop the traffic for installation and on-site maintenance, and the electrical system is more reliable. Though this vehicle vibration-based bridge health monitoring has hardware advantages, it faces significant analysis challenges. On one hand, the vehicle bridge detection system is a complex transient dynamic system with many components, parameters, and uncertainties. So it is therefore impossible to accurately model the physical system. Recently, data-driven approaches become popular because they can get rid of the requirements of prior knowledge about the physical model. However, in indirect approaches, the data is noisier as it is further from the source, and more taps of noise involved. Thus, we need a lot of data for training data-driven approaches. Moreover, different bridges have distinct characteristics, such as geometry, dynamic properties, and etc., leading to different distributions of vehicle acceleration signals. Therefore, directly applying supervised models trained on available data to other bridges may result in significantly worse performance. This means we will need more data to be able to monitor multiple bridges, but it is time-consuming and impractical to obtain vehicle vibrations with corresponding bridge damage labels from every bridge. So after all, to overcome the above challenges, Our goal is to extract a feature that is sensitive to bridge changes or damage and invariant across different bridges. So in this work, we introduce a novel framework for vehicle vibration-based bridge health monitoring. And we first pre-process the input vertical acceleration signals of the vehicle traveling over the bridge for denoising, alignment, and resampling. The pre-processed signal are input to two modules, signal decomposition module and system identification module. The signal decomposition module decomposes the signal to extract the damage-sensitive feature using a synchrosqueezed wavelet transform-based method. And we will show why we use this specific method later. The system identification module estimates the domain-invariant factor using an expectation maximization algorithm-based method. And then we will obtain a damage-sensitive and domain-invariant feature by dividing the damage-sensitive feature by the domain-invariant factor. And finally, we extract feature. The extracted feature will be used for localize and quantify bridge damage. So given limited time, I will concentrate on the signal decomposition module and show how we obtain the damage-sensitive and domain-invariant feature. To find the damage-sensitive and domain-invariant feature, we derived the theoretical formulation of a vehicle bridge interaction system. This formulation, the secondary derivative of y, is the vertical acceleration of an oscillator traveling across a simply supported homogeneous beam. We observe that some terms in the equation cannot be domain-invariant. For example, the first term, the dominant frequency of it, equals to the resonant frequency of the vehicle, which is omega sub A. So this term is not domain-invariant across different vehicles. Similarly, these terms contain the resonant frequency of the bridge. So they are not domain-invariant across different bridges. And now let's say the last term. It does not have frequency components of the vehicle and the bridge. And it has some interesting properties. First, phi is empirical shape functions. It is a superposition of intrinsic mode functions, which is based on a function oscillating, which is basically a function oscillating around zero. And it has time-varying magnitude and time-varying instantaneous frequency. For example, this figure shows an empirical mode function, intrinsic mode function, that is sine 0.1 t times cosine t. So second, this secondary derivative of phi contains information about model curvature, which is very sensitive to damage. Discontinuities of model curvature can reflect local damage such as cracks on the bridge. Lastly, this C5n is domain-invariant factor. It is a constant that depends on system parameters. And it can be estimated using the expectation maximization algorithm in the system identification module. Therefore, after dividing the domain-invariant factor, we can obtain our desired feature, which is damage-sensitive and domain-invariant. We denote this desired feature as y sub d. In summary, y sub d is within a low frequency bandwidth that includes the driving frequency n pi v divided by L, where v is the vehicle speed, L is the bridge length. Because this frequency is generally lower than 1 Hz, y sub d does not overlap with other dominant frequency components, such as resonant frequencies of the vehicle and the bridge. So right now, we formulate our problem as a signal decomposition problem that decomposes the non-stationary vehicle acceleration to extract y sub d by reconstructing the non-stationary component within the driving frequency bandwidth. And the solution to this problem, we introduce to use synchrosqueezed wavelet transform to represent the signal first and reconstruct the feature using the inverse transform. Why does it work? There are 3 reasons for using the synchrosqueezed wavelet transform. On one hand, this transform decomposes a non-stationary and time-varying signal as a superposition of intrinsic mode function type components. This perfectly match the properties of our desired feature. And on the other hand, this transform enhances frequency locations for denoising, and compared to empirical mode decomposition, synchrosqueezed wavelet transform is based on wavelet transform and does not have the mode mixing problem. So to evaluate the effectiveness of our damage sensitive and domain invariant feature, we conducted numerical experiments using finite element models. We built 5 models with 5 different bridges that have different lengths, stiffness, and frequencies. We introduced local damage to these models by reducing the stiffness of a 0.6 meters element. The damage severity levels vary from 10% stiffness reduction to 60% stiffness reduction. And the damage location varies from 0.1 span of the bridge to 0.9 span of the bridge. In order to add stochastic process for testing robustness, random forces following Gaussian distributions are applied on every node of the finite element model. We first visualize different features for showing if our feature is damage sensitive and domain invariant. For each subplot, x-axis is the normalized location on the bridge, and y-axis is the magnitude of features. Different line styles represent different bridges. We plot 3 features from left to right. The inverse synchrosqueezed wavelet transform without normalized by the domain invariant factor, C5N, and the second is the inverse continuous wavelet transform, and the third one is our feature. And from top to bottom on each subplot, we plot the feature with 3 damage cases that have different severity and locations. Ideally, we want to observe that we can localize and quantify the damage by simply visualization. For instance, if the damage is localized at the 3rd quarter span, we expect to see a peak or a cave at the 3rd quarter span on the feature. And for more severe damage, the absolute value of the feature at the damage location should be larger. And in addition, to show the domain invariant property, the ideal feature should have the same shape for the same damage case and different bridges. This figure clearly shows that our feature is the most damage sensitive and domain invariant feature of the ones we tested. So besides visualizing the feature to verify the damage sensitive and domain invariant properties, we also ran a Monte Carlo simulation with different noise added to the models for testing the robustness of our feature. We ran 2 tasks. One is a supervised damage localization and quantification tasks that train a model using available data and predict damage on a test site for the same bridge. The purpose is to see if the feature can capture the damage information. In other words, if it is damage sensitive. The second task is a semi-supervised damage diagnostic task, which uses the feature from one bridge to train a regressor and predict damage on data for the other bridges. The purpose of this evaluation is to test the domain invariant property of our feature. The x-axis on the plot is different diagnostic tasks, location, localization, or quantification. Y-axis is the root mean square error. Lower error means better performance. We test different time and frequency domain frequency features and with our feature. We can observe that our feature have the smallest error for all the tasks. Means it is the most damage sensitive and domain invariant feature of the ones we tested. Although future works are required for testing the scalability and feasibility of this framework, especially on real-world systems, we can draw some conclusions now. In summary, we introduced a physics-guided framework that extracts the damage-sensitive and domain-invariant feature from vehicle accelerations. This feature can be used for localized and quantified damage occurring on different bridges without using labels. We evaluate the effectiveness of our feature on numerical experiments, and our feature outperforms many time and frequency domain features. Thank you, and if you have any questions, please send an email to me.